Hi and welcome to the 9th and final part of this Advanced C# course. I was going to end the Advanced C# course with an example of creating an ASP.NET MVC web application using C#. The more I delved into writing the tutorial on ASP.NET MVC, the more I realized that ASP.NET MVC at least demands its own video series. So I'm currently working on a video series where we'll build an ASP.NET MVC web application using C#. I'll bring these videos to you as soon as I can. As I had originally intended, I'm going to finish the Advanced C# course focusing on the topic of C# reflection. So let's get into it. Let's first gain a basic understanding of reflection, and then we'll write a code example using the reflection technology in C#. So, what is reflection? Reflection provides objects of type that describe assemblies, modules, and types. You can use reflection to dynamically create an instance of a type, bind the type to an existing object, or get the type from an existing object and invoke its methods, or access its fields and properties. If you are using attributes in your code, reflection enables you to access them. For content like this and much more, please consider subscribing, and please ring the bell so that you'll be notified of future content. If you like this video at any point, please give it a thumbs up. It will be greatly appreciated. In the 8th part of this Advanced C# course on C# attributes, we used the reflection technology to read metadata provided through the use of our own custom attributes from relevant program elements. When I say program elements, I'm referring to classes, methods, fields, properties, etc. So reflection allows the developer to access metadata within .NET assemblies at runtime. .NET assemblies are self-describing entities, which means the metadata data about the relevant assemblies reside within the assembly itself. So at runtime, we are able to load a target assembly and read its metadata using reflection. Using reflection, we are able to, for example, instantiate objects from classes that reside within the target assembly and invoke the relevant object's methods or get and set the relevant object's property values. So in this video, we are going to create a code example that will serve as a test harness. We are going to create code that loads a target assembly and displays a list of relevant classes that reside within the target assembly. We can then select an item in the relevant list that represents a class and test the functionality within each of the class's methods. The important thing to note here is that in this example, we will not reference the target assembly from within the project that contains our calling client code. We are using reflection to late bind to the classes that reside within the target assembly, so that we can instantiate objects and test the object's functionality at runtime. Note that when I refer to the target assembly, I am referring to the assembly that contains the functionality we wish to test through our test harness. We will be using what is known as late binding to test the methods that reside within the relevant classes contained within the target assembly. So, what is late binding? When we reference an assembly from a project through, for example, Visual Studio, and subsequently write code to instantiate an object from a class that resides within the referenced assembly, this is known as early binding. When we reference an assembly like this, the compiler has information about the target assembly at compile time. Late binding occurs when we don't set a reference to a target assembly at compile time, and we instantiate an object from a class that resides within the target assembly at runtime. The obvious disadvantage to late binding is that late binding is prone to runtime errors. When early binding is employed, the compiler has relevant knowledge, for example, relevant type information about the target assembly's constituents at compile time. So compile time errors can be flagged and corrected at compile time. Potential errors are averted at compile time, and therefore certain runtime errors are avoided. With late binding, reflection can be employed to gain necessary information about the target assembly itself and its constituents at runtime. So let's create our test harness code example where we'll use late binding to test the functionality that resides within a target assembly. Let's create a .NET Core Console application named Test Harness. Let's create a .NET Standard library project named Utility Functions. The Utility Functions project will be compiled into our target assembly. Now, it is important to note that I have included the Utility Functions project, which of course, when compiled, is compiled into a .NET assembly, in the same solution as the .NET Core Console project where we'll write our calling client code. This is important to note because we are not going to explicitly reference the Utility Functions assembly from the .NET Core Console project. So if we were to early bind to the Utility Functions assembly, we would reference our Utility Functions project like this. But let's cancel this dialog box because we are going to load the Utility Functions assembly at runtime using Reflection. We are not going to set a reference to it at compile time. We want to late bind to the Utility Functions assembly at runtime. This is obviously just a mock example and not a real-world application. But you can see how we could put a number of assemblies within a directory, traverse the assemblies within the relevant directory, and automate the testing of functionality within the target assemblies at runtime. We would not have to reference any of these assemblies within our test harness project, because using Reflection, we can access all the information we need for each assembly and test the functionality within the assemblies. So the advantage of this loose coupling of our test harness application with the assemblies that we are testing is that we don't need to early bind to the assemblies at compile time. We can simply put an assembly or assemblies in an appropriate directory, and our test harness application can learn about the assembly or assemblies at runtime by accessing the relevant assemblies metadata at runtime through Reflection. But we will simplify this example and focus on classes within a particular namespace within one target assembly. Our target assembly in this case will be the Utility Functions assembly. If this doesn't make sense to you at the moment, please bear with me, and this will become clearer as we progress with creating this code example. Let's include basic functionality within our Utility Functions project. Once completed, this project will be compiled into an assembly which will serve as our target assembly, i.e., the assembly against which we'll perform our reflection functionality. Through the use of Reflection, we'll be able to read relevant information about the assembly, instantiate objects from its classes, and test its methods. So, let's write the code for the Utility Functions assembly. Let's start by deleting the class that was auto-generated by Visual Studio. Let's add a class named Basic Utility Functions. Within the Basic Utility Functions class, let's create 4 very simple methods. Let's create a method named WriteWelcomeMessage. The WriteWelcomeMessage method contains no parameters and returns a welcome message as a string. Let's write a method named integer+integer. The integer+integer method contains 2 integer parameters and returns an integer value. The returned integer value will be the mathematical result of the first integer argument plus the second integer argument. We can appropriately name our parameters operand 1 and operand 2 respectively. Let's write a method named concat3strings. This method contains 3 string parameters and returns a string value. The returned string is a concatenation of the arguments passed into the concat 3strings method. The order in which the string arguments are concatenated is the order in which their corresponding parameters appear in the relevant parameter list, from left to right. Let's write a method named getStringLength. It contains one string parameter. This method returns an integer value, the character length, of the string argument passed into the getStringLength method. And that's it. That is our very basic utility functions class completed. Let's create another basic class. Let's name this class Basic Math Functions. Let's create two really simple methods in this class. Let's create a method named divideOperation, which contains two parameters of type double. This method returns a value of type double. That is the result of a divide mathematical operation. In this method, the second argument is divided into the first argument, and the result of the divide operation is returned to the calling code. Let's create a method named multiplyOperation, which contains two parameters of type double. This method returns a value of type double. That is the result of a multiplication mathematical operation where the first number argument is multiplied by the second number argument. The returned value will be the product, which of course is the result of the multiplication of the first number argument by the second number argument. Okay, so we now have two classes in our utility functions project. So now we want to be able to decorate certain program elements with a custom attribute that we can use to provide additional information to the calling code about the relevant program elements. In this case, the program elements will be classes and methods. Let's create a custom attribute named Information Attribute. For more information on custom attributes, please view the previous part of this course, which is a tutorial entitled C# Attributes. I have included a link to the relevant video below in the description. So, in order to create a custom attribute, the relevant class must inherit from the system.attribute built-in class. Let's keep this class really basic, so let's add one auto-implemented property named description. This property will enable us to provide a custom description about a program element that we'll decorate with our information attribute custom attribute. We want to constrain our information attribute custom attribute to the decoration of only class and method program elements. So we can do this by decorating our information attribute custom attribute class with the attribute usage built-in attribute. We can then pass the following bitwise operation to the constructor of the attribute usage built-in attribute. So let's pass attribute targets.class or attribute targets.method to the constructor of the attribute usage built-in attribute. So this means that only classes and methods can be decorated with our information attribute custom attribute. So next, let's apply our custom attribute to the relevant classes and methods. Let's go to the basic utility functions class and let's decorate the class itself and its methods with the information attribute custom attribute. So let's set the description property for our custom attribute declared against the basic utility functions class to this class contains basic utility methods. Let's set the description property for our custom attribute declared against the writeWelcomeMessage method to this method returns a welcome message. Let's set the description property for our custom attribute declared against the integer plus integer method to this method returns the sum of two integer operands. Let's set the description property of our custom attribute declared against the concat 3strings method to this method concatenates 3 strings in the same order as they appear in the parameter list from left to right. Let's set the description property for our custom attribute declared against the getStringLength method to this method returns the character length of a string argument. So let's move on to our basic math functions class. Let's decorate the basic math functions class with our information attribute custom attribute like this. So here the description property is set to this class contains basic math functionality. Let's decorate the divide operation method with our custom attribute, where the attribute's description property is set to this method divides the first number by the second number and returns a result of this divide operation. And lastly, let's decorate the multiply operation method with our custom attribute and set its description property to this method multiplies the first number by the second number and returns a result of this multiplication operation. So we have included in the metadata for our utility functions assembly very basic descriptions about method and class program elements through the use of our information attribute custom attribute. Now let's write the calling client code. So in the calling client code, we want to provide functionality that targets a particular namespace within the target assembly. In this case, our target assembly will be the utility functions assembly and reads all the relevant information about the assembly's classes and methods that are members of the relevant namespace. We'll create functionality where the user can choose a class from a list of classes that reside within the relevant namespace. Once the user has chosen the class that the user wishes to test, the user can then choose a method from a list of methods that are members of the relevant class. The user can then select from a list of methods the method that the user wishes to test. Once the user has chosen the method that the user wishes to test, the user is prompted for values for each of the parameters contained within the relevant method's method definition. Once the user has provided values for all the relevant parameters, our code will invoke the method, and the result returned by the method is displayed to the console screen. So you can see that this test harness application can be used to test functionality within an assembly. Note that you can extend the code that we are about to write to traverse a number of assemblies within a directory and automatically test particular functionality within the assemblies. So you could write your own automated test facility based on the code we are about to write. For the purposes of this tutorial, however, the code will be simplified. So let's write the code for our test harness project, which is our .NET Core console project. The first thing to do is within our calling client code is include a using directive to the system.reflection namespace, like this, so that we can make use of reflection in our application. So let's start writing our code in the main method. Let's first create two local string constants. The first constant stores the target assembly file name, utilityfunctions.dll. The second constant stores the target namespace that contains the classes that the user will be able to test through our test harness application. So the namespace is utility functions. Let's write the code that will load the target assembly at runtime. So we are using the assembly.load method to do this, but we may need to replace this with the assembly.load file method. When we test and debug the code later in the tutorial, we'll know which method needs to be employed here, either the load or load file method. So we'll leave it as load at this point. We pass in the path of where the target assembly will be in order to load the target assembly into memory. So later in this tutorial, just before we test our code, for the sake of simplicity, we'll copy the target assembly into the same directory as where the assembly for this project will reside. So let's write code here to point to the path of the target assembly, which will be the current directory, the same directory as where the test harness assembly will reside. Let's use the path.combine method to combine a path with the name of the file. The path class resides in the system.io namespace, so let's include a using directive to the system.io namespace. So we are able to get the current path from the appdomain.currentdomain.base directory property. This is the directory where the assembly that we are currently working on will reside. Let's pass this value as the first argument to the path.combine method. Then let's pass the name of our target assembly, which is utilityfunctions.dll, as the second argument into the path.combine method. The return value from the assembly.load method will be the object of type assembly. So let's assign a variable of type assembly, the value returned from the assembly.load method. So we have now got a reference in memory to our target assembly. Let's write code to get a list of classes from the target namespace within our target assembly. So the namespace within our target assembly is named utility functions. So let's use link to get a list of types or classes from within the utility functions namespace. Let's ensure that we have a using directive to the system.link namespace. So we can use the assembly object's getTypes method to return a collection of classes that reside within the target assembly. We can use the where method to filter on the assembly's utility functions namespace, like this. Let's assign the returned result to a generic list that is strongly typed as system.type. Then let's convert the IEnumerable collection returned by the link query to a list, and we can do this by using the toList conversion method, like this. Let's write a method that encapsulates writing a prompt to the user. Let's write code to display a message prompting the user for input to the console screen. As you can see, we are prompting the user to press a number key to indicate to the application which class the user wishes to test. So it is better to encapsulate this prompting functionality in a method that we can reuse for this purpose throughout the creation of this application. This method encapsulates the functionality of displaying text to prompt the user for input to the console screen. So next we want to write code to display a list of classes to the console screen so that the user can select the class that the user wishes to test. So we can simply write code that traverses the items stored in the classes list, which contains the result of our link query, and output the relevant class names to the console screen in sequential order. So let's do this. In our list of classes, each class name is preceded by a number, which will allow the user to press a number key to select the class that the user wishes to test. Let's write the code where the user can press a number to select a class from the classes list. Let's use a switch statement to return the relevant item from the list. So now we want to create an object instance from the user's chosen class or type. We can use the activator.createInstance method to do this. And here we are writing code to late bind to a class within the target assembly. We can assign the returned object from the activator.createInstance method to a variable of type object. You can see that when we late bind like this, we do not have the benefits of type safety, so code like this is prone to runtime errors. This highlights a disadvantage of late binding like this in code. So because at compile time, we don't know the type that will be returned at runtime by the activator.createInstance method, we need to use a variable of type object to reference the returned value. So we have now written the code enabling the user of our application to choose a class from a list of classes by pressing a number key associated with the relevant class. Once the user has chosen a class, the user will be presented with a list of relevant methods. Let's write code to clear the screen once the user has chosen the class from the list of classes. Let's write a method where we can encapsulate code to output a heading to the console screen. On the screen that displays a list of methods belonging to the class that the user has selected, we want to include a heading at the top of the screen containing the class name that the user has chosen. Let's go to the main method and write the code to output the relevant heading to the console screen. Let's write code to prompt the user to choose from a list of relevant methods. We now want to write code to output a list of relevant methods to the console screen. So logically, the code to present the user with a list of methods is exactly the same as the code that presents the user with a list of classes. So we have an opportunity here to refactor our code by creating a reusable method that encapsulates functionality to output a list of both classes and methods. So this will be one block of code that can output a list for both classes and methods. In this method, we need to account for the difference between the type representing a class and the type representing a method. In this context, classes are of type system.type and methods are of type methodinfo. So to solve this problem, we can apply generics. Let's create a method named displayProgramElementList. Let's include the t placeholder between greater than and less than symbols to indicate that this is a generic method. Let's base the code for this method on the code that we have already written in the main method to output a list of classes. You can see that we are writing this code in a more generic style because this code will output the items of a generic list that is strongly typed as system.type and a generic list that is strongly typed as methodinfo. Great. So let's replace the code in the main method that outputs a list of classes with a call to our display program element list method. The type that represents a class in terms of reflection is system.type. We have another opportunity to refactor our code because the code to return an object of type system.type from our list of classes or types logically is the same as the code to return an item of type methodinfo from a list of methods. So let's write code to encapsulate this functionality in a method named returnProgramElementReferenceFromList. So we need to include generic functionality within the method definition of the returnProgramElementReferenceFromList method. We also need to return a value of type t from this method. And we can copy the code for this method from our main method and paste it into our returnProgramElementReferenceFromList method. So let's replace the code in our main method that enables a user to choose from a list of classes with a call to the returnProgramElementReferenceFromList method. So let's call the getMethods method on the typeChoice object, which represents the class that the user has chosen from the relevant list, and assign the returned value to a generic list that is strongly typed as methodinfo. Note that a generic list that is strongly typed as system.type is used to store references to classes or types, and a generic list that is strongly typed as methodinfo is used to store a list of methods. We can now reuse the displayProgramElementList method in our main method to display a list of methods. We can pass in the methodinfo type to the relevant type parameter, but we don't actually need to do this here because the compiler has enough information to determine the type. Let's call the return program element reference from list method, which will enable the user to choose a method from a list of methods displayed to the console screen. Let's write an if statement to check if the method info object returned from the return program element reference from list method is not null. Let's write code to clear the screen. Let's write code to output a heading containing the class name and the method name of the class and method that the user has chosen to test. So the next step is to prompt the user to provide a value for each parameter of the relevant method. So we are able to get a list of parameters from the relevant method by implementing the method info object's getParameters method like this, and we can assign the returned result to an array of type parameter info. The next step is to invoke the method chosen by the user and pass in the relevant parameter values that will be provided by the user's input, i.e. if the relevant method contains any parameters. If the relevant method does not contain any parameters, the method can be invoked without any arguments passed to it. So let's encapsulate the functionality for this in a method named getResult. In order to execute the functionality for the getResult method, we need the relevant class instance object, the relevant method info object, and the array containing the relevant array of parameter info objects. So in the getResults method definition, let's include a parameter of type object to accommodate the class instance. Let's include a parameter of type method info to accommodate the relevant method to be executed. And let's include a parameter that accommodates an array of type parameter info. So the invocation of our method is going to be different in terms of code implementation when the method that is invoked requires a number of arguments, to when the method requires no arguments passed to it, i.e. the relevant method's method definition contains no parameters. So let's create an if statement that checks to see if the parameter's argument contains any items. If it does not contain any items, we can call the method info object's invoke method and pass null into the second argument. The first argument must be passed an argument that references the appropriate class instance. This class instance or object contains the method that we are invoking here through this line of code. The else part of the if statement invokes a method that does contain parameters. So we must write code to prompt the user for a value for each parameter. So let's create a method that allows for an argument which will contain an array of parameter info objects to be passed to it. So let's name this method return parameter value input as object array. Let's create a one-dimensional array named paramValues and provision the array to hold a number of items equal to the number of items stored in the array passed into this method, i.e. the array of type parameter info. Let's create a counter variable named itemCount and initialize it to a value of 0. Let's create a for each loop to loop through each item in the parameters array. Let's write code to prompt the user to enter a parameter value. So let's say that we know that the parameter type can only be one of the following: string, int, or double. So let's write an if statement to check the type of the relevant parameter. If the parameter is a string, then no type conversion of the console.readLine method value is necessary because this method returns a string. So we can then write code to assign the user's input to the relevant position in the parameter values array. So the code for when the relevant parameters of type int or double is slightly different. We must include an explicit type conversion from string, returned by the console.readLine method, to the relevant type before assigning the inputted value to the appropriate position in the param values array. We must increment the item count variable by 1 for each iteration of the loop. In the location in our code editors where the loop has exited, we can write the code to return the param values array to the calling code. Great! So let's go back to the getResult method and call the return parameter value input as object array method. Then we can write code to invoke the relevant method and pass in an array argument containing the user's input for each parameter as the second argument to the method.Invoke method, like this. As stated earlier, the first argument passed to the invoke method is the relevant instantiated object, instantiated from the class that the user has chosen to test. To finish this method off, let's write the code to return the result returned by the relevant method to the calling code. Let's then go to the main method and call the getResult method. Let's write the code to display the returned result from the getResult method to the console screen. Great! Before we test the code, let's compile our two projects. Let's find the target assembly and let's copy the assembly to our clipboards. Then let's go to the directory of our test harness project and paste the target assembly into this directory. Let's test our code. Okay, so we have a little bug here. So I suspect this is because we need to use the load file method instead of the load method. So let's change the code accordingly. Let's run the code again. Great! We can see our classes displayed in a list, but our information attribute custom attribute class is also present in the list, and this is not desirable. We don't have any methods in the information attribute custom attribute class to test. So, if we select one of the classes that we wish to test, like, for example, the basic utility functions class, we are presented with a list of methods, which is great. There are some methods listed here that we are not interested in testing, like, for example, the equals method or getHashCode method. These methods belong to the object class, which, as we know, is ultimately the base class for all types in C#. So we only want to test the methods that perform functions directly related to the class we have selected, in this case, the basic utility functions class. We'll modify the code to filter out undesirable code elements in a bit. For now, let's continue with our test. Let's select the integer plus integer method. Oh, we should be receiving a prompt to enter a value for each of the parameters contained within the integer plus integer method. So we have another bug to fix. So here's where we need to fix the bug. I forgot to include the prompt text in the return parameter value input as object array method. So let's include a prompt for each parameter item. Let's test the code again. Let's select the basic utility functions class from our list of classes. Let's select the integer plus integer method. So we are now prompted to enter a value for the first parameter. Great. So let's do that. Let's enter 5. We are then prompted to provide a value for the second parameter. Let's enter a value of 6 for this parameter. Once we press the enter key, the correct result of 11 is presented to us. Great! So except for the fact that certain program elements that we have no desire to test are appearing in our lists, the basic functionality of our test harness is working as expected. So let's write the code to filter out those unwanted program elements. We are going to use the information attribute custom attribute for this purpose. Let's say that we only want those program elements that are decorated with our information attribute custom attribute to appear in our lists of program elements to test. So let's write a method that checks to see if a program element, i.e. a class, or a method is decorated with the information attribute custom attribute. If the program element is decorated with the information attribute custom attribute, we want to include the relevant program element in our list of program elements to test. If, however, the program element is not decorated with the information attribute custom attribute, we must exclude the relevant program element from our list of program elements to test. So let's write a private static method named hasInformationAttribute. And let's include one parameter within its method definition. This parameter will represent the program element that we need to check. So we need the hasInformationAttribute method to check if the information attribute custom attribute has been declared against the relevant program element. In the context of the requirement of this application, the program element can either be a class or a method. So the parameter must be of a type that can accept a class or a method as an argument. In this particular case, those types will either be of type system.type or of type method.info. We could include two methods named hasInformationAttribute and differentiate their method definition, where each method definition contains a parameter of a different type. One version of the hasInformationAttribute method can contain a parameter of type system.type, and the other version of the method can contain a parameter of type method.info. So we could use method overloading to perform the desired check for if a custom attribute has been declared against a program element, i.e. either a method or a class. However, we can achieve what we want with only one version of the hasInformationAttribute method, because the system.type and method.info types both inherit from a common class, the member.info class. If we right-click the text in our code editors representing the type class and select Go to Definition, we can see that the type class inherits from the member.info class. If we do the same thing against the method.info class, we can see that the method.info class also inherits from the member.info class. If we look at the member.info class definition, we can see that it contains a method named getCustomAttributes, and this is the method we need to use to check if the relevant program element is decorated with the information attribute custom attribute. So the point is we don't need to overload the hasInformationAttribute method. We can simply define the parameter for the hasInformationAttribute method as member.info in one method. This will mean we can pass both types of arguments to the hasInformation method, i.e. an argument of type system.type, a class program element, or an argument of type method.info, a method program element. So let's look at the code for the hasInformationAttribute method. We have created a local string constant to store the name of the type of our information attribute custom attribute. So this name includes the namespace of where the information attribute custom attribute resides, a full stop, and the attribute class name. We have written code to loop through all the custom attributes that may be declared against the program element type passed into this method. As you can see, we are able to call the getCustomAttributes method for both class and method program elements in our method, because the system.type class, which represents class program elements, and the method.info class, which represents method program elements, both inherit from the member.info class, which contains the getCustomAttributes method. Within our for each loop, we first get the type of the current attribute. So we have written type attrib equals attrib, the current attribute object, dot get type. We then check to see if the name of the type attribute is equal to the information attribute custom attribute's name. If it is, this means that the information attribute custom attribute has been declared against the program element type passed as an argument to this method, so we can return true to the calling code. If all attributes have been traversed and none of the attributes match our information attribute custom attribute, this means that the program element passed as an argument to the method does not have our information attribute custom attribute declared against it, so we must return false. So this method can be used in our calling code to filter out program elements based on whether or not the relevant program element is decorated with the information attribute custom attribute. So how can we use our method for this purpose in our main method? The answer is we could modify the relevant link queries to include our hasInformation attribute method. And we can include our hasInformation attribute method in the relevant where filters. So let's first modify the link query for returning a list of class program elements. We can simply include a call to our hasInformation attribute method in the where filter method like this. To filter out methods that aren't decorated with the information attribute custom attribute, we can modify the appropriate link query like this. Let's test our code. Excellent. You can see that only those classes in our target assembly that are decorated with the information attribute custom attribute appear in the relevant list. If we select the basic math functions class from our list of classes, we can see that its methods that are not decorated with the information attribute custom attribute have been filtered out of the relevant list. Great! Let's also include functionality to appropriately output to the console screen the description property value of the information attribute custom attribute for our relevant program elements. In terms of the user's experience, this functionality will provide additional information about the classes and methods that the user wishes to test. So let's write a private static method named returnInformation custom attribute description. This method returns a string and contains a parameter of type memberInfo. Remember, both the system.type class and the methodInfo class inherit from the memberInfo class, so this method can be reused for both class and method program elements. We want to read the description property, so let's create a local string constant that references the text description. Let's create a for each loop that loops through the custom attributes that may have been declared against the relevant program element, which in this case will either be a method or a class. So within the loop, let's reference the attribute type like this. We can then apply an if statement to check if the current attribute is the information custom attribute. Okay, so let's refactor our code here so that the target information attribute type constant can be accessed from both this method and the hasInformation attribute method. If the current attribute is the information custom attribute, then let's access its description property. We can do this using a reflection like this. So we are attempting to check if the property info object is not null, but the compiler is complaining. This is because the project is currently built on .NET Core version 3.1. Checking for nulls like this is only allowed in a later version of C#. So I'm going to change the version of .NET to .NET 5 for this project. Great, and you can see now that this line of code is now supported, i.e. using the isNotNull line of code. But I'm going to use the old way of checking for nulls anyway, just in case the followers of this tutorial are using an older version of .NET for their projects. So we have now written the code to read the description property from objects derived from the relevant information custom attributes that have been declared against relevant class and method program elements. So let's write the code to appropriately output the program element descriptions declared through the use of our information attribute custom attribute to the console screen. Let's create a method named display_element_description for this purpose. This method only needs one parameter, which will be the text we wish to output to the console screen. Let's write code to check if the argument passed to this method is not null. If it is not null, let's write its value to the console screen using a different background and foreground color to the default console screen colors so that the text stands out. Then let's use the console.resetColor method to reset the color back to the default console foreground and background colors. Let's go to the main method and use the display_element_description method to output the relevant program element descriptions to the console screen. So we can pass the result of the return information custom attribute description method into the display_element_description method on one line like this. This code will display our custom descriptions of the program elements that the user wishes to test. Let's test the code. Okay, so we are getting a bug, and this is because the load file method cannot find the target assembly. The reason for this is because when we changed our version of .NET for the test harness project, a new directory for .NET 5 was created. This directory contains the assembly for the test harness project, but it doesn't, of course, contain the target assembly. So let's copy the most recently built utility functions assembly to the .NET 5.0 directory. Let's run the code again. And you can see that our custom elements are displayed, and we are able to test the functionality of methods and classes that reside within our target assembly. We have used the reflection technology to accomplish this. You can also see that additional information about the relevant program elements is outputted to the console screen. This was made possible through the use of our information attribute custom attribute. Excellent! To finish off the application, let's add code to enhance the user's experience. As you may have noticed, once the user has tested a method, the application automatically ends. We currently have no way of navigating back to the first screen where we are presented with a list of classes that we may wish to test. We want the user to have the option of returning to the list of classes so that the user can carry on testing other classes and methods. So we can do this by putting the relevant code within an infinite loop. Once the user has tested a particular method, the user can either press, let's say, the spacebar key to end the application, or any other key to return to the screen that contains a list of classes. Let's test the code. Excellent. So the last thing I'd like to bring to your attention is the technology encapsulated in the system.Reflection.Emit namespace. Using this technology, a developer is able to generate code dynamically. So the developer is able to generate dynamic methods or even dynamic assemblies on the fly. The user could, for example, generate intermediate language code on the fly based on user input. So because of functionality like this, you can see how incredibly powerful the C# language is. I recommend navigating to this location to read more about this powerful aspect of Reflection. I hope you've enjoyed this tutorial on C# Reflection. We have now come to the end of this advanced C# course. If your Reflection provides objects of type that describe assemblies, modules, and types. You can use Reflection to dynamically create an instance of a type, bind the type to an existing object, or get the type from an existing object and invoke its methods or access its fields and properties. If you are using attributes in your code, Reflection enables you to access them. We demonstrated using Reflection to create an application that can serve as a test harness. The test harness allows a user to add a target assembly to the same directory where the test harness application resides, and choose a class that the user wishes to test from a list of classes that belongs to a specific namespace that resides within the target assembly. When the user selects a specific class from the class list, that class is instantiated into an object through the use of late binding. This is how the test harness is able to test the functionality within a target assembly without referencing the target assembly at compile time. In the test harness application, Reflection is employed to instantiate the relevant class into an object. When an assembly is referenced by a project at compile time, this is known as early binding. With early binding, the compiler has relevant information about the types within the target assembly at compile time. Late binding is used when the compiler does not have compile time knowledge of the target assembly. So, a technology like Reflection is used to access the relevant information about the assembly, which allows for late binding to occur at runtime. It was noted that late binding has the disadvantage of being prone to runtime errors. When early binding is employed, a specific type can be instantiated into an object using the new operator, and we have the advantage of compile time type safety. We do not have the advantage of compile time type safety when late binding is employed in code and the activator.create instance method is used to instantiate an object from a type. Lastly, we briefly discussed the technology encapsulated within the system.Reflection.Emit namespace. Functionality for generating intermediate language code or IL code dynamically resides within the system.Reflection.Emit namespace. A developer can use the functionality within the system.Reflection.Emit namespace to create code for dynamically generating methods and even assemblies at runtime. For content like this,